In this video, I want to look at this cylinder that's rolling down an incline, and I want to find its acceleration and its angular acceleration. And I want to do this two different ways. The first way is I want to assume it rolls without slipping. And the second way, I want to assume that it slips. And both of rolling without slipping and slips have different assumptions that we make. But we start them off both the same way. So we start them both off with a free body diagram. Now on this free body diagram, I'm going to have my normal force. My normal force acts normal to the plane. I'm going to have a weight force. My weight force acts straight down, and it's equal to mg. And if I'm rolling clockwise and I'm moving this way, my friction is going to oppose that motion, and it's going to act back up the plane. So that's my frictional force. Now I'm also going to break up my weight into x and y components. X going down this way, y we can say is going up this way. And we'll say that's positive, so this is going to make sure that my angular acceleration matches up with my acceleration of my center of gravity. And the two components I have is going down, I'm going to have mg times the cosine of theta, and this way is going to be mg times the sine of theta. And again, all of these forces except the frictional force actually go through this main point right here. So I should probably draw this a little bit better. But we know they all go through that point. So now I have my free body diagram. I want to use my equations of motion. So my equations of motion starts with Newton's law, where I have the sum of my forces is equal to mass times acceleration of my center of mass in the x direction. Going down the plane is going to be positive. So that means mg times the sine of theta minus my frictional force is going to be equal to this mass times its acceleration. Okay, let's go towards the next equation. The sum of my moments is equal to I times my angular acceleration. And we want the sum of the moments about point G, which is the center right here. Now, like I said, everything goes through this except the frictional force, and it's a distance of r, a radius away. So I'm going to have my frictional force times r is equal to I times alpha. And finally, because we roll without slipping, that means the relationship that we're going to use is my acceleration is going to be equal to r times alpha. And what I can do is I can just sort of back substitute now. I can get that alpha is going to be equal to my acceleration over r. So I can put that right here. My frictional force times r is equal to I times a over, and we'll write this as a capital R, r squared, over r. Then when I divide this r right here, I get over r squared. So my frictional force is equal to I a over r squared. Now we can substitute this back in here. When I do that, I get mg times the sine of theta minus I a gx over r squared is equal to magx. So let me rearrange this. I'm going to still have mg times the sine of theta, but now I'm going to have magx plus I agx, and look at that, they both have a term of agx, so I can get mg times the sine of theta is equal to m plus I think I lost my r squared, so I lost that r squared, times AGX, and I can divide this. So this is part of my answer. AGX is equal to mg times the sine of theta divided by m plus I over r squared. But we know what I is. We know that I for a cylinder is 1/2 mr squared. So let's put that in. So this is going to be equal to mg times the sine of theta over m plus 1/2 mr squared over r squared. They're going to go away. So now we're going to have m plus 1/2 m. So that's going to be equal to mg times the sine of theta over 3/2 m. And this is going to cancel here. So this is going to be equal to 2/3 g times the sine of theta. And that's my acceleration of my center point. So now I can actually bring this back up here and get that my angular acceleration is going to be equal to 2/3 g over r times the sine of theta. And that's my angular acceleration. So let me box these in. This is my angular acceleration, and this is my acceleration of the midpoint g. So now I want to redo this problem, but instead of not slipping, I want to say it slips. So the assumption here is my frictional force is going to be equal to some coefficient of kinetic friction or dynamic friction, we'll call it UD, times the normal force N. Okay, so let's go. We actually use the same free body diagram, so that makes it easy, but we have to use different equations of motion. We're going to use the same governing equation, so the sum of the forces in the x are equal to mass times this acceleration. And we'll have, again, going down is positive, we'll have mg times the sine of theta minus the frictional force is equal to mag times x. And we have this expression right here. We know that the frictional force is mu dn. So we'll have mg times the sine of theta minus mu dn is equal to magx. And we actually, if we look at the sum of the forces in the y, we're not accelerating in the y. So this is just equal to 0, and it becomes a statics problem. N minus mg times the cosine of theta is equal to 0. So n is equal to mg times the cosine of theta. So finally, we get mg sine of theta minus mu d mg times the cosine of theta is equal to magx. Well, look at that. The m's cancel. And if we solve this, we're going to get g times the sine of theta minus mu d times the cosine of theta is equal to agx. And that's my acceleration when this rolls and slips. But we have one more thing to find, and that's going to be the angular acceleration. So we're going to go back to the sum of my moments are going to be equal to I times alpha. And we want to solve for alpha. So what's the sum of my moments? Well, it's the frictional force times R is equal to I times alpha. We already know what my frictional force is. My frictional force is this right here. So I'm going to have minus, it's not a minus, but mu d mg cosine of theta r is equal to, well, we know what this is. We know that this is my inertia is 1/2 mr squared times alpha. Now divide this over. When we divide this over, we get this is equal to 2 mu d mg cosine of theta r over m r squared. M's are going to cancel, one of the r's are going to cancel, and our final angular acceleration is going to be equal to 2 mu d g times the cosine of theta over r. And there you have it. Here's the angular acceleration if we slip. So this is with slipping. This is my acceleration. This is my angular acceleration for slipping. And over here, this is my acceleration for no slip. And this is also my acceleration, my angular acceleration for no slip.